Okay, let's look at the learning system. We are now here, 11.3. So today I'm going to talk about high-level description language, and namely Verilog language. And remember that we have a second quiz 3 weeks from now. So please try to catch up. The second quiz is around the 15th week, and the final exam is the 17th week. And we will have a decent class, free to join. Okay, up to you.
我跟你说，第二小考在第14还是第15周？
第14周。对。
谢谢。
第14周。All right, let's start talking about Verilog. So why do we need to learn Verilog? Verilog is one of the two popular languages used in hardware design, IC design nowadays. In Taiwan, Verilog is more popular. In US and some other countries, VHDL is more popular. The language Verilog originally is not a design language, no. It's for simulation. It's a modeling language for a very efficient, event-driven digital logic simulator. It means that we have this language to verify that our hardware design is correct. And that's it. Okay, when it's presented, it's only for simulation. But sometime later, people found that it can be also used as a design language for IC design. It puts into use as a specification language. Spec language means that it's not only for simulation, it's also for specification. When you specify your hardware design using this language, there's going to be a tool, which is a compiler, that can compile your Verilog code into a circuit, a file. You can use that file for manufacturing. And this way, you can automate the design process. Will become very efficient, very convenient to design hardware. You don't really need to draw the layout because it's too tedious, too much consuming. Instead, we use Verilog code. It's just like writing C or C++. That will make your hardware design very, very efficient. Okay? So now, Verilog is one of the two most commonly used languages in digital hardware design. The other one is VHDL. Okay? VHDL is more formal, is more verbal, is more, you have to cut more stuff to make sure that it's a very sound design. Meaning, when you debug your code, typically Verilog is probably easier, prone to making error because it does not require too many like typing. It can be implicitly declaration. So from formal language point of view, VHDL is probably better. But from efficiency point of view, if smaller code, it will be easier to code for your design. Virtually every chip nowadays, FPGA, ASIC, and so on and so forth, is designed in part using one of these two languages because it's too time consuming. If you want to draw a layout for custom design for complete chip, no way. Consume too much time, maybe 1 year, maybe 2 years to design a chip. It's too slow. So that's why more and more people use this kind of how to discrete language for their IC design. And in the language, it combines structural and behavioral modeling style. There are two given styles. One is structural style. The other one, behavioral style. We will talk about that in a few minutes. So let's look at this example. This circuit is a multiplexer using logic gate, right? Inverter, AND gate, OR gate. Okay. A, B, and cell is 3 input signal. F is output signal. So if you still remember from the unit, you know that from 2 to 1 multiplexer, when selection, when cell is 0, F is going to get what? Get A, right? Remember that? If cell is 1, you're going to get B in the output. So for example, here, then you're going to get 0. It's 1, you're going to get 1, and so forth. That's 2 to 1 multiplexer. The cell is a control signal, or in general, input signal, to decide what the output F will get, either A or B, depending on the value of cell. 0, you get A will go through. Cell is 1, B will go through. That's 2 to 1 multiplexer. And how many gates do you have? 1, 2, 3, 4. 4 logic gates. And this 4 logic gate is very basic, it's primitive logic gate. It's built-in in Verilog language. You don't have to design, you don't have to describe what the AND gate or inverter or OR gate is. Okay? You don't have to specify, you don't have to describe, because it's built-in. You can simply use AND gate, OR gate, inverter directly in your Verilog code. So for example, the next. Module is just like a function or procedure. The function in C language describing what this module is doing. We declare that this module is called mux. Mux is a module type, module name. And like in C language, F, A, B cell are parameter. Okay? Typically, output signal will be given first, and then input signal. So F is output, A, B cell are input. And actually, if you don't declare that, fine, Verilog accept. If you don't declare F, A, B cell are input output signal, but we prefer declare implicitly, because it will be easier to debug, it will be easier to read. So output F, input A, B cell. Right? It's multiplied in this interface, 4 wires, okay, in this small circuit. And now, AND or NOT. As I said, these are primitive or primitive gate that's provided by Verilog code automatically. You don't have to describe this small module. This is a primitive logic gate. So AND G1, G2, meaning we have 2 AND gates here. One is G1, the other one G2. Both are AND gate. Okay? Both are AND gate. And use common to separate them. And semicolon for termination for this statement. So if you can see that G1 is here. And for AND gate, there are 2 input, there are 1 output. So F1, A and cell, meaning F1 is output. A and N cell are the input. Is A, is N cell. This internal signal is N cell. So that describes your gate interface and the connection with the other circuit. In OR gate, there's only one instance here. AND gate is a function is a module, is a primitive. And G1, G2 are two instances. OR gate, likewise, OR gate, G3 is an OR gate with F output and F1 here, F2 here for the input. So then you know that, okay, this gate input connected to the output of G1, right? Because they have share the same name. F1 is here, F1 is here. So you know that G1 output would be G3's input, right? NAND gate here, G4, N cell is output, cell is input. So when you provide these three statements, you describe how these gates are connected, right? It should be very clear. Okay. And then end module. Finish the module description. Any question here? Module may contain structure, instances of primitive and other module. Not just primitive. You can also call the other module. Maybe so just like the C program, routine can call many functions, right? And each function can also call the other function. Okay. And again, in each module, you can call primitive. You can also call other module. Any question? Identify, not explicitly define default to Y. We know that, okay, F, A, B cell are Y, input Y and output Y. But N cell and the F1, F2, these three names, three identified, are not explicitly declared. Then it's default to Y. These are Y. If there's no declaration for these three names. Okay. Any question? All right. With the same circuit, this description is not the only way we can express it. There are more than one way to describe a circuit module. In here, we try to use high-level description, which is called behavior model. We can use all statements to describe 2-to-1 multiplexer without using any gate. There's no gate at all, but we just describe it with the behavior, with the operation. So let's look at it. OR A, meaning this is a block. The second block, A or B or cell, meaning if A or B or cell, this input signal changes. Either one changes. Then you have to do this. You have to re-evaluate. You have to recalculate this statement. If cell is typical C statement. If cell is 1, it's true, then B assigned to F. Otherwise, meaning cell is 0, then A assigned to F. So that's exactly 2-to-1 multiplexer, right? 2-to-1 multiplexer. But here, we describe the circuit using like C-like language, C-like description. And here it says that module may contain one or more OS block. It's only one OS block, but actually you can have more than one. You can have more than one OS block. And their name can be share to indicate the Y connection. We call them sensitivity list. Contain signal whose chain triggers the execution of the graph. When A or B or cell change, any one change, from 0 to 1 or 1 to 0, you have to do this again to get the new value of A. Right? So that's exactly what this two-to-one multiplexer do, right? When A, B cell given some specific value, you get A, right? But if one value change, one input change, you have to redo, you have to re-evaluate to get a new value for A. Okay. So this is another way to describe multiplexer. Any question? And we notice that now N is declared red. Red is simply for register. But you probably don't understand. F is not register. F is a wire, right? F is a wire, not register. But in Verilog, red is a storage component for simulation. For doing simulation, you do a simulation based on A, B cell value, you get F value. Okay. After you do the simulation. But only when A or B or cell change, then you re-evaluate. Otherwise, F will keep the old value, will keep the previous value. Although there's no storage component, there's no flip-flop, there's no register, but we treat it as a simulation-based storage component, storage signal. You can remember the previous value until you evaluate the circuit. And the body of all graph, okay, contain traditional imperative code like F assign some expression. Any question? Another way to describe math is continuous assignment. Also very convenient. We describe the two-to-one multiplexer by using assignment statement. Assign A equals cell question mark A column B. What does that mean? Again, it's just like C language, right? C statement. We assign A is called continuous assignment. We continuously assign the value to A based on the following equation. When the cell is true, which is 1, A assigned to A. When the cell is 0, means false, then B assigned to A. That's exactly what this two-to-one multiplexer does, right? Left-hand side is always set to the value of right-hand side. Right-hand side is typically an equation. Any change on the right-hand side will cause re-evaluation. So that is a continuous assignment which can describe a conventional circuit. Any question? Another one. In here, it's a module description, yes, but it's also for primitive. The reason why we use primitive is in two-to-one multiplexer is very common. You're going to use this component very, very often in many, many places. Then why not try to treat it as a primitive, just like AND gate, OR gate, equals OR gate. That was very convenient for you. So we describe the primitive is called user-defined primitive. It's not library primitive. It's not AND gate, OR gate. It's a user-defined primitive. After you describe like this, you can use it and treat it as a typical primitive in the library. So primitive math It's actually again, it's a module. We use truth table to describe the input-output relationship. 1 question mark, 0 meaning if your input A, B cell in order, A, B cell fit the pattern, 1 question mark, 0. So 1, 0, 0 or 1, 1, 0 fit this pattern, then you get 1, the output. If you look at the value here, this 1, this 0 is cell. When cell is 0, A will give N, right? So A, here A is 1, so output has to be 1 if cell is 0. Alright? Okay. And this means that 0, 0, 0, you get 0 in the output. 0, 1, 0, you get 0 in the output. So this describes the pattern for the input.
它那个 input 的那个顺序啊，1问号0那个，它是按照第3行的那个 input 还是 max 定义后面的那个 input？
第3行，对吧？
不是最上面，最上面，就是它是按照这个定义的顺序，还是你放到 module 里面的那个顺序？就是它的左边不是3个数 input 吗？对，那你刚刚说是按照 A、B， 然后 cell 的 in order 的顺序，就是顺序这样下来。
对，就是这边。
是上面的那个，还是第3行的那个？是宣告的顺序，还是上面丢进去参数的顺序？
以这个为主。
以上面的为主。
Right. The question is, what is the order of the input signal? Well, you have to follow the order in the parentheses, A, B cell. Not the order in the declaration here, the type. Okay. Any other question? Okay, you might find that actually they might. Let me check. They could be okay. So here, this pattern and this pattern. You have 0, 0, 1. 0, 0, 1 fit this pattern, also fit this pattern, right? It's okay. It doesn't matter. As long as you have a consistent value in the output, it's fine. And actually, for simulation, it will going to match from top to bottom. Look at the first pattern, okay, no. Then second, no. Third, no. Fourth, yes. Okay, then you get 0. You don't have to check the other pattern anymore. Okay. What I'm saying is that for vector code, the output value for simulation is simply check 1 by 1 in sequence. If you fit, you match, then you get the output. You don't have to check the other pattern at all. No more. Okay. So just simply go through from top to bottom and try to cover all the possible cases. Don't leave some cases undefined. Otherwise, you might encounter some problem. Let me repeat it. This pattern should cover all the combinations from 0, 0, 0 to 1, 1, 1. The 8 pattern should be covered in this pattern. Otherwise, you're going to have some circuit issue that will include some flip-flop in the circuit, which is not we want. We simply want to have the value defined, and the modular description, the truth table, should cover every combination, every case. And that's for primitive. you have to use truth table. No other way to define user primitive. Only truth table, because that will make solution much faster. What I'm saying is, if you have module here, no, you cannot do that. Only primitive. You have to use truth table for primitive. For module in general, any other style is okay. Should be fine. Okay. Here we say that when A and B match, cell is ignored. Simply meaning that both A and B are 1. The output has to be 1. No matter what value cell is, right? No matter you choose which one, you get 1 in the output because both are 1 input. From well, actually, we don't have to really understand the meaning, but just give you some idea. All right, this is important. How are simulators used? You describe, you design in system module. This is your design. We call that system model. And the test bed is just like test equipment. The equipment issues signal for the input of the system model, and you get output for response. And the test bed can check the output whether or not it's correct. So test bed is just like a hardware equipment, testing equipment to test your circuit, provide input and look at the output whether or not it passed your test. So test bed generate stimulus and check response, coupled to model of the system, the design model, and pair is run simultaneously. Both are integrated, and then we run at the same time to make sure that your design is correct, your design is verified. Okay, and as I mentioned, there are 2 different styles in the vendor code. And actually that can be mixed. What is structural modeling? Structural modeling is just like we describe a circuit using logic gate and flip-flop to construct our circuit. It's called structural modeling. When Verilog was first developed in 1984, most logic simulators operated on NAND disk. So the NAND disk is simply a list of gates and how they are connected. And we call that NAND disk. It's a natural representation of a digital logic circuit. N gate, O gate, inverter, and how they are connected. This is your NAND disk. Although it's not the most convenient way to express test bench. So in test bench, we typically don't use structural modeling. We will use the other one, which is called behavioral modeling. Okay? Because it's easier to write the statement to generate the signal. Behavioral modeling is a much easier way to write test benches. It's also good for more abstract model of circuit, not only for test bench. You can also use behavioral modeling in your design model. Okay. It's easier to write, and it also simulates much faster, and it's more flexible. It provides sequencing. So if you want to have high productivity, you might prefer to use behavioral modeling. And then you want to make sure that your design using this kind of logic gate, so on and so forth. Whether it's successful in part because it allows both the model, behavior model and structure model, and the test bed to be described together. So that said, virtually nowadays, almost every application specific integrated circuit is designed using either Verilog or with HDL. Behavior modeling with some structural element. And since we try to write a Verilog code or HDL and compiler, for example, Synopsys is a company. Synopsys Design Compiler is a translator that can translate your Verilog code into named list. Okay? Named list gives you how the circuit is designed using logic gate, basic component. And design using Verilog similarly to that. Before you do the synthesis, you have to try to verify your code is bug free. So you will do a lot of simulation to make sure that the design is logically correct. The functionality is correct. After the simulation, you do the synthesis, try to compile, try to translate from Verilog code to a named list. So named list generated, and based on generated named list, you can do some static timing analysis to know that to estimate what is the delay based on a specific process, like 90 nanometer process. You can get how much time per delay on your circuit. So that's it. There are two different styles. One is behavioral, the other is structural. The behavioral is concurrent event-driven trigger processing, event-driven simulation. And typically is an initial block or point block. We'll give you some example. In each initial OS block, there's imperative code that can perform standard data manipulation tasks. For example, you can say that A equals A or B, something like that. That's a typical imperative statement. Or if then, okay, these are typical C statement, right? Processing 1 until they delay for a period of time or wait for triggering event. We'll give you some example in a few minutes. The other side is structural. Just give you the structural model example for portable multiplexer using basic logic gate. Verilog program built from module with I/O interfaces. We call that structural style, structural modeling. Module may contain instances of other modules. Just like in each procedure, you can call the other procedure. In the function, you can call the other procedural function, so on and so forth. Module contain local signal. Can declare, just like you can declare local variable in the procedure. Again, in here, module can contain local signal, like any cell, F1, F2. These three are local variable, local signal. And we did not declare them because in Verilog code, implicitly, they are wild. Okay? If they are wild, you can omit the declaration for these three variables. Simply y. And module configuration is static and all run concurrently. So you have to distinguish between when we describe a module here, it's just like we describe a function in C language. But when we call that procedure, when we call that function, when we call that module, it becomes an instance. Right? You know that, right? The instance can be called, can be involved in many, many places in your code. Just like, so for example, if this is a multiplacer module, we can call that module like max, like x, y. When in some statement we have max, x, y, meaning that we call the module multiplexer. There are two instances, and each instance this is the input-output interface signal name. This, right? In VLSI, net or wire, they're simply name of wire, name of signal of wire or net. To present connection between things. For example, gate, input output signal of a gate. Do not hold their value. Okay? They do not hold value. Like N cell, like F1, F2, these are wire. They cannot contain, they cannot remember the value. The signal simply propagate on a wire. Going through, right? But it cannot remember the value. Okay? Cannot latch the value. Only flip-flop or latch can remember the value. Or memory. Take their value from a driver, such as a gate or other module. The signal value comes from the output of a logic gate or some module, right? Just like I say, you get a cell is coming from the output of the inverter gate. F1 is a wire, the signal comes from the output of the G1 logic gate. And N is also the wire, the net. That's for the output of this module. So this is for net or wire. For red represents data storage. It can remember the value. It behaves exactly like memory or register or flip-flop in a computer. Hold their value until implicitly assigned in an initial or OS block. Okay. we repeat it. It can remember, it can hold the value 0 or 1. It could more than 1 bit. Until we implicitly assign the new value in the initial or OS block. And red can be used to model logic, flip-flop, and so on and so forth, but do not correspond exactly. But we will going to talk about that in a few minutes. Red, for simulation, you remember the value, but in real, in the implementation, it may not be the flip-flop or register. No, it could be just a wire. Just like example we had here, and actually it's not a flip-flop or register or latch. No, it's just a wire. But the reason why we declare that red is, for simulation point of view, the value will keep the old value until you will evaluate, reassign the new value to that variable. Discrete event simulation. Let's say when the language is proposed, is presented, it's for simulation purpose. The basic idea only do work when something changes. We try to do the simulation based on the input value change. Then we do the evaluation to get the output value. Centered around an event queue in the simulation implementation, there's an event queue. Event queue contain event labeled with the simulated time in which they are to be executed. Let me give an example. Okay, here we have 3 input and 1 output. When you do simulation, event-driven simulation, we try to look at the input. Okay, here we have 0, 1, 1. We do simulation. So the AND gate input 0, 1, you're going to get 0, right? The output of the AND gate. And with 0 here, 1 here, then we get 1 in the output. And that's it. But from event-driven simulation point of view, it also involves delay. So for example, the AND gate is 2 nanosecond. Is 3 nanosecond, for example. For simulation, in a simulation, we will schedule an event after 2 nanoseconds to evaluate the AND gate and get 0. Okay? There's going to be an event for AND gate. You'll get the output value after 2 nanoseconds. And then, after you get this 0, because this one already available in the beginning, so 0 and 1, you schedule an event for all gates. And after 3 nanosecond delay, you can get the output here. So, in this time, simulation time, during the beginning of simulation, after 2 nanoseconds, there's an event queue. There's event. After that, after 3 nanoseconds, there's another event to simulate for the whole gate. And you might even have like this is 1 nanosecond. Okay, this event And at the same point of time, there could be more than one event at the same time. Then you have to do the simulation for all of them. And that can produce another event. So for example, this event for AND gate. After it's done, it's going to trigger AND gate event, trigger OR gate event. Right? And then the time of the clock of the run to here, we do the simulation. And after a inverter is done, there's no more new event. And then after 2 next second again, we do simulation for OR gate. After that, everything is done. No more event. Or even we can have like this, something like that. Then what? AND gate is 2 seconds. So after it's done here, you're going to schedule another event in here for AND gate. Okay, so on and so forth. Until every event is done for simulation, it becomes overdone. We can look at the output for the result. So the idea is that it's centered around an event queue, contain event labeled with the simulation time, okay, at which they are to be executed. In real hardware operation, actually, input signal continuously evaluated to get the output value. The output value keep changing based on the input. Every minute, every second, every nanosecond. But for simulation, you cannot do that. It's impossible to simulate for continuous time. It has to be discrete event. It has to be discrete time. We only do simulation at here, at here, at here, and at here, and stop. You are not going to simulate every nanosecond because that's going to consume too much time, and actually it's not needed. Only at this 4 point of time, you change the output possibly. Basic simulation paradigm. Execute every event for the current simulated time. Doing this change system state, the value could be changed. And may schedule event in the future. For example, this available now, and you can trigger 2 more events for inverter and for OR gate. Okay. And when these 2 are available, it triggers the AND gate event. When there are no events left at the current time, instant, at the one simultaneous time, show this event in the queue. When this is done, the next one will be here. This done, the next one will be 2 nanoseconds after it here, here, until everything is done. Okay, let's take a break.